On some of the homework, on, I believe, the third section of chapter 4, where you're asked to confirm whether something's a vector space or not, there are 10 things that need to be checked out to confirm whether something is that something is a vector space. Now, if you can show that just one of those things isn't so, then you don't have a vector space. But you need to check all 10 things, and you need to know what 10 things to check. So to help classify these, we have properties related to closure, we have properties related to distributive laws, we have properties related to associativity, we have properties related to the existence of the zero element, and we have the inverse property. Now this is only one property and this is only one property, but there are multiple distributive laws that need to be checked, and associative laws and closure properties, not instead of laws, properties. Okay, so I'm not going to recite what the 10 criteria are. You need, in doing the homework, to go down through all 10 and check each space, each proposed vector space, against each of the 10 properties. Now, that assumes that you do have a vector space. If the proposed vector space isn't a vector space, then by having checked those 10 properties on a variety of examples, you're going to be in a position to more easily spot the flaw in any proposed vector space. In other words, you can often pretty well home in on whatever it is that's not, whatever property is most easily shown to be violated. Okay, so let's just do an example of something that actually isn't a vector space. Be the set of x, y, z such that x equals y plus z plus 1. Now, a vector space, you need a set of scalars, and you need an operation. The operation here will implicitly be addition, and the set of scalars will implicitly be the real numbers. Unless we say differently, we're going to use addition and real numbers, okay, for the operation and the set of scalars. Okay, so, well, we have this set. Now, we start by understanding what this tells us about the ordered triple x, y, z. Okay, it tells us that x is the sum of y and z and 1. So I asked everybody to write down an example, or a couple of examples, of ordered triples that satisfy this, and people did real well with that. So a few of the examples we had were 1, 0, 0, because y is 0, z is 0, y plus z plus 1 is 0 plus 0 plus 1, and that's what x has to be, and that's what x is. Okay, another example, 3, 1, 1. Y is 1, z is 1, so y plus z plus 1 is 1 plus 1 plus 1, that's 3. And sure enough, x equals 3. And you can check the same thing here. 2 and 2 and 1 make 5. Okay, now, that's just to get a little feel for what these entities might look like, for what these ordered triples might look like, okay? And the idea is very simple. This number has to be one more than the sum of these two numbers. Now, the question is this closed? Well, the answer is very clearly no. Okay? And we can see that very easily just by taking any two of these. If we add this to this, we're going to get 4, and 0 and 1 is 1, 1. We're going to get 4, 1, 1. So 1, 0, 0 plus 3, 1, 1 is 4, 1, 1. 1, 0, 0 is in the space. 3, 1, 1 is in the space. But 4, 1, 1 is not in the space. Can you check that? Well, it's very simple to check that. 1 and 1 is 2. Well, y is 1 and z is 1, so y plus z plus 1 is 1 plus 1 plus 1, which is 3. But x is 4. If we add these two, x is 4. So right now we know, or already we know, that this is not a vector space. Okay? Now there are other properties that are potentially violated. Okay, what about a zero element? Is there something we can add to x, y, z to get x, y, z? Okay, well, the only thing we can add to x, y, z is to get x, y, z is 0, 0, 0. So the question mark here, the question mark has to be 0, 0, 0. The thing we add to x, y, z to get x, y, z is very clearly 0, 0, 0. Yeah, so if there's a zero element in this set, it's 0, 0, 0, but y plus z plus 1 for this element would be 0 plus 0 plus 1, which is 1. And that is not the x-coordinate of this, is it? The x doesn't equal the y plus the z plus 1. So, and our conclusion is that the zero element, the element that would have to be the zero element, isn't in the set. So there's no zero element. Okay? What about scalar multiplication? Scalar multiplication is violated. For example, just as one simple example, 1, 0, 0 multiplied by 2 gives you 2, 0, 0. 1, 0, 0 is in the space. 2, 0, 0 is not, because 0 plus 0 plus 1 is 1, and x is 2. So this space is not closed under scalar multiplication. Okay, well, we'll look at a different space here, something that might actually be a vector space. We'll kind of check it out.